Okay, let's go. We're ready.
No, hold on.
So last time we covered a lot of important stuff. We spoke about the equivalence theorem, which is important. We also spoke about inverses. So we spoke about guys that are invertible. What was the definition? What does it mean to be invertible?
There exists a matrix
There exists a matrix,
where
so a n by n. There exists a matrix that we call a inverse. It's also going to be an n by n such that
A inverse by A gives you the identity. And
Alright, so invertible means there exists a matrix that when we perform matrix multiplication with A, in any order we get the identity. We also spoke about the fact that there's a theorem that says once one of these equations hold, the other one will automatically hold, so you only need to check one. But that's what invertible means. It means that there exists such a matrix that makes this work. If there doesn't exist such a matrix that makes this work, it's called non-invertible or it's called singular. Tell me some things that are equivalent to A is invertible. What are some things we know about A? Just throw them out.
Determinant of A is non-zero.
We know the determinant has to not be 0.
the reduced row echelon form of A is the identity matrix of size n.
What would be the alternative to that? There are only two cases for any matrix is reduced row echelon form. Remember? It's either going to be the identity or
It
we'll have a row of zeros. Right? So in the case that you get the identity, it's actually going to be invertible. In the case you get a row of zeros, it's not going to be invertible. What else do we know about a matrix if its inverse exists?
There's a unique solution for each row.
Right, so if I look at the system AX equals B, it has a unique solution. By the way, this also means, we spoke about homogeneous equations before, AX equals 0 has only the trivial solution. Right? That is, X must be 0 in that case. Right? So we spoke about homogeneous, that they're always consistent. At minimum, it has this solution, but possibly it has infinitely many solutions. But if your A is invertible, then this has only a unique solution, so it has to be the trivial one. Anything else we know about invertible matrices? What else do we know?
Like that, another equivalent thing?
Yeah, an equivalent thing. If I know A is invertible, what are some things I know about it?
A is the product of elementary matrices.
I can express A as E1 times E2 times blah, 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 up to EM, where the EI are elementary. What does it mean to be an elementary matrix?
It's a matrix or when a row operation is performed on the identity.
Okay, so if you take the identity matrix and you perform a single row operation as we define the row operations, the matrix that you obtain is called an elementary matrix. What is special about elementary matrices?
They're invertible.
They are invertible. Every elementary matrix is invertible and its inverse is also elementary. What else?
They store information about the row operation performed.
They store information about a row operation, which means if you take this guy and multiply by any matrix, the result will be performing the same row operation on that matrix that you performed on the elementary matrix to create it. So they give us a concrete way to express a row operation being performed.
Actually, I have a quick question I realized I never asked. An elementary matrix is just a single operation. I mean,
Yeah, just one.
Okay.
So you start with the identity, you do one thing.
Okay.
You can do anything that's
Sure.
allowed, but you do one thing.
I see. And then obviously you can't doing a row operation on an elementary matrix. It doesn't necessarily produce a Like, okay, so you have an elementary matrix and you do another row operation on that. That's not an elementary matrix.
Yeah, the result of that won't be another.
Okay.
Yeah. So it has to start with the identity and you do one operation.
Okay.
Question?
And by the way, we proved, for example, that, I was talking to someone about this today, that the product of a bunch of invertible matrices is also invertible. And we proved that by induction. But it turns out knowing this gives you an alternate version of that proof, right? If I have a bunch of things multiplying and I know each is invertible, I know that each can be expressed as a product of elementary matrices. So the huge product is just a huge product of elementary matrices, which will happen if and only if it's invertible. So it's an alternative proof to that. Did someone have a question?
Yes.
Yeah.
You said that a type 1 operation is equivalent to doing several type 3 followed by a type 2.
Yeah.
So how can they all be expressed as elementary matrices? If one is like a repetition of the other ones.
Because we defined row operations. Remember, our row operations were defined by an inspiration from solving systems. So it's the idea of, here are the things we can do when solving a system. We isolated those things and defined them as row operations. It turns out one you could describe as the others, but there is no restriction on that.
Does that mean you can also get like a certain elementary matrix as a product of other elementary matrices?
But yeah,
Specific cases,
that
not
by definition, pretty much. Elementary matrices are invertible, which means they would satisfy this condition, which means they themselves are a product. And in the trivial case, it would be itself, right? In the abstract definition of a product, having one guy is a product, right? So yeah, these are some things we spoke about. We also spoke about a way to compute the inverse. So we know what the inverse means. We know things that is equivalent to finding an inverse, but how to actually compute an inverse. So if I give you a matrix, how do we find the inverse? We spoke about that. There was a row reduction method. To compute a inverse. And what was that? What did we do?
You augment A with an identity matrix of size n, and you continue to perform row operations on A
Until what point?
until you get an identity matrix.
Until you get the identity, which by this theorem is going to be the reduced row echelon form. So all you do is just augment this and find the reduced row echelon form. And we had a proof of a theorem that the same operations that takes A to the identity will also take the identity to the inverse of A. And we proved that using, again, elementary matrices. So they're a very neat kind of proofing tool. Okay? So this was one operation, and we actually did an example. We did two examples of this with a 2x2 and a 3x3. I'm going to show you the other way to find inverses to A. Which honestly, I don't know a nice way of it coming about. It's just an observation. I don't know why, who's the first guy who noticed it, why he noticed it. But it's just something that, oh yeah, if I compute that, I see that I'll get the inverse. But why would you think of computing that in the first place? As far as I know, I don't think there's a nice geometrical meaning or anything like that. But it is an important kind of matrix anyway, and it's called the adjoint matrix. So now we're going to look at the second method to compute an inverse. It's called the adjoint. Let me define what an adjoint is for you. Definition. Let A n by n, and again, it's always square matrices. Those are the only guys that have determinants and are possibly invertible. And we kind of already know that that has to be the case because the theorem tells us they have to reduce the identity, and that's going to be a square matrix. That can only happen if it's square anyway. So this would be a matrix. The adjoint, I'm defining this, of A, which we denote to be or defined by, the adjoint is just going to be, it's also going to be an n by n matrix of where the entries are given by Cij, where Cij is the ijth cofactor. And then we're going to take the transpose of that. So we're going to go through the matrix, and each element we're going to replace it by its cofactor. Then we're going to take the transpose. Like, why someone decided to do this at some point, I'm not exactly sure, but it turns out it works out beautifully. So it's the transpose of the matrix of cofactors. You replace each element with its cofactor. And remember what the cofactor was. It was just, for that element, block out everyone in his row and his column, find the determinant of the matrix that results, and apply the sign according to that sign chart. So that was the cofactor. Now if you do that for every element in a matrix and replace it by the determinant, that cofactor, and then you take the transpose of it, that new matrix that you create will be called the adjoint matrix. And it turns out, and this you can do by direct computation, that A inverse will be 1 over the determinant of A times the adjoint of A. Proof by direct computation. Which we'll leave to the reader. We can show that A times determinant of A. You can show that, right? You take a matrix and multiply by this particular matrix, it turns out you'll end up getting, you'll obtain a matrix where on the diagonal, you just end up with the determinant of A the whole time. And zeros everywhere else, right? And you'll see that by direct computation. And so basically what we can do is, assuming A inverse exists, I can multiply by A inverse on both sides. The determinant will be non-zero, so I can divide by the determinant, and then I'll obtain this one. So let's actually do that. In fact, what I'm going to do is I'm going to use this to prove a formula that the book gave you, the determinant of a 2 by 2 matrix. Example. Assume A equals A, B, C, D is invertible. Find a formula for its inverse. So what I'm going to do here is, let's find the adjoint of it. I'm pretty sure they use an uppercase A. Let's find the adjoint of it. So what is that going to look like? Well, remember there's a checkerboard pattern of signs, so there's always a plus in the top left. There'd be a minus here, there'd be a minus here, and there'd be a plus here. And in each of these parts here, we're going to put a cofactor, and we're going to take the transpose of that, right? So this is the position of A. So what we're going to do is we're going to replace that with a cofactor of A. Block out everyone in his row and his column. You get the determinant of this. The determinant of a 1 by 1 matrix is just going to be its value. Right? So let me write that so you don't confuse that with absolute values. Then you go over here, block out everyone in that column, you get a C, and so the term is just going to be that value. Go to the C position, block out everyone in that column, you get a B. Go to the D position, block out everyone in that column, you get an A. Then we can take a transpose of that. So you get the first row becomes the first column. DC. So it's a plus D minus C. And the second row becomes the second column. That's the adjoint. Right? In other words, a lot of people just memorize, oh, just change the signs of those guys and switch the diagonals on those guys. They just memorize what you're doing to find the adjoint. And it's not so bad to memorize it for a 2 by 2. So this means by the formula, A inverse is equal to 1 over the determinant of A times the adjoint of A. And this ends up being 1 over AD minus BC times this matrix. Swap the guys on the main diagonal, negate the other guys. And of course we can check this in general. If I take AB, CD and multiply that by D minus B minus C A, and factor out the scale AD minus BC. What I would get is multiply this by this, AD minus BC. This by this, you get minus AB plus AB. This by this, you get CD minus CD. This by that, you would get AD minus BC. This will give you 0, that will give you 0. And then when I divide by this expression, those two give you a 1. And so we end up with the identity. So that's going to be the inverse for any choice of A, B, C, D, such that this number is not 0. So you're not dividing by 0 when you do this. So you can use this formula to do the first example that I gave you for the other method, but let's do the second example I gave you for the other method using the adjoint. Find A inverse using the adjoint method. If our A is this guy. This is the guy we did last time. 1 minus 2, 3, 2 minus 1 minus 1 minus 3, 1, 4. Let's find its inverse, which I think we did last time. Hopefully we didn't make a mistake and we can verify it. Did anyone actually verify our answer last time? Because the row operations took forever, so we wanted to make sure there wasn't like a sign mistake or something like that. I actually wrote down the answer here, so we can know we're right. Just to double check. So let's actually do that, what that would look like with this method, how we would find the inverse. We will start by finding the adjoint. Okay, so let's start by finding the adjoint of it. One big matrix transpose. What matrix? The matrix of cofactors, which means plus sign here times some determinant, minus sign times some determinant, plus sign times some determinant, minus sign times some determinant, plus sign times some determinant, minus sign times some determinant, plus sign times some determinant, minus sign times some determinant, plus sign times some determinant. Okay, let's fill in these determinants. Okay, so each element we will replace with its cofactors. So now we're in the position of 1. So block out everyone in that row in that column. We get this, minus 1, minus 1, 1, 4. Go to the position of this minus 2. Block out everyone in that row in that column. We get 2, minus 1, minus 3, 4. Block out everyone in this row in this column. 2, minus 1, minus 3, 1.
Is it minus 2?
Come again? Here?
Oh, no, sorry.
No, that's
My thing was to do the other, but okay.
Here, we're in this position. Block out everyone in his row in his column. Minus 2, 3, 1, 4. Now we're in this position. Block out everyone in his row in his column. 1, 3, minus 3, 4. This position. Block out everyone in that row in that column. 1, minus 2, minus 3, 1. This position. Block out everyone in that row in that column. Minus 2, 3, minus 1, minus 1. Now we're in this position, block out everyone in that row in that column. 1, 3, 2, minus 1. And finally, we're in this position, block out everyone in that row in that column. 1, minus 2, 2, minus 1. Let's simplify these, and we're going to take the transpose and see what we have left. So this will be minus 4 plus 1, right? That's minus 3. And you take the plus sign, so it stays minus 3. This would be 8 minus 3, right? That's a 5. Take a minus sign, so this is minus 5. This would be 2 minus 3. That's a minus 1, and it keeps up the plus sign, keeps it as a negative. Here, minus 8 minus 3, that's minus 11 times a minus, so that's positive 11. 4 plus 9, that's a 13. 1 minus 6, so minus 5. And then we took a negative sign, so that's a plus 5. 2 plus 3, that's a positive 5, and it keeps the positive sign. Minus 1 minus 6, that's a minus 7. Take a negative sign, so it becomes a positive 7. Minus 1 plus 4, positive 3. Take the transpose of that, that's going to be minus 3, minus 5, minus 1, 11, 13, 5, 5, 7, 3. Determinant of A was what? We found that last time. I think that was 4. Was it 4? Positive 4, negative 4?
Positive 4.
Previously found. Which means now that our A inverse will be 1 over 4 times that matrix. Minus 3, 11, 5, minus 5, 13, 7, minus 1, 5, 3. Was that equal to the answer we got last time? Well, that's the right answer. So we should have gotten this last time. But we probably wrote it like minus 3 over 4, 11 over 4, 5 over 4, minus 5 over 4, 13 over 4, 7 over 4, minus 1 over 4, 5 over 4, 3 over 4. So you can check, but I mean, the likelihood of us getting both exactly the same answer using two different methods and they're both wrong, it's not great. But we'll play with the probability on this. That's the correct answer anyway. But that was the correct answer. I checked it. I checked it on my own. I don't want to do it in class. Okay. So those are two different methods. In general, I will not force you to do one method over the other. I showed you two methods. You can choose whichever method you want. Personally, as a student, I didn't like the adjoint method. But in hindsight, I can't say that was the right thing to do. Like, this was probably, like, this was easier than doing all those row operations, right? Mm-hmm. It's like when I was learning 346 the first time, like I would always mess up on row operations. Right? I hate arithmetic. It's just not, it's not interesting to me. My brain checks out while I'm doing it, so I'll always mess up with it. So when I was doing linear algebra and we learned about row operation, I'm like, okay, it's addition, subtraction, or whatever. I'm doing homework and I'm always getting the wrong answer. I'm like, damn it! So I really worked hard on row operations. I became a row operation master. And so like, whenever there's an option to use a row operations, I just do that and ignore everything else. Because I worked so hard to get good at it. You know, so, but in hindsight, that's probably wouldn't have been the way to go. This is easy enough in most cases, I think.
Which one's better for higher, or which one's worse?
It's a personal choice. See, it really matters. I can't definitively say one is better or the other. You might have a matrix where in two row operations you get it to be the identity.
No,
it's
like,
just you can't.
say that like for bigger matrices, like that would be like nested determinants, right?
Yeah. But still, for a bigger matrix, you're always going to have like a lot of row operations anyway. Yeah. It's going to be competition intensive no matter what. It's just that it's a personal choice, whichever one you want to do. I would never ask you to do something bigger than a 4x4. And in a 4x4 case, probably I would do row operations. In a 3x3 case, it's a toss-up. I wouldn't really say one is better than the other.
On the test, can we just do it either way, or do you
Yes, that's what I said. I will never force you to do one way or the other. Choose the way you like and do it that way. I will just ask you, find an inverse, use it to do blah. Find the inverse however you want, and do blah. So these are two methods. It's up to your personal preference what you want to pick. As a student, I always did the first method, but that's because I worked so hard to get good at the arithmetic, and I hate memorizing stuff, so if I can derive something, I'd rather do that than memorize some extra formula. So what's an adjoint? I don't care. That's an extra definition that I don't need, because row reduction will work. Which is, it's a very stubborn habit to have, but for a math person, it's kind of, at least early on, I think it's a good habit to have. The idea that I don't want to memorize something, I just want to know how to figure it out, right? It's a good, it helps you practice a lot of things. Like you can construct things easier eventually. So that's it for inverses. That's how we find it. Those are all the things I want to tell you about inverses at the moment. One thing else I want to define for you is just symmetric and skew-symmetric matrices. Pretty much I'm going to give you a definition, we're going to move on. I might make a couple comments about them. Symmetric matrices are very important, but we never get far enough in the text where we're actually using them. But it's things that you should know about, and you should have some familiarity with what they are and how to do little manipulations on them, how to prove little properties that they have. So we are going to talk about symmetric and skew-symmetric matrices. Essentially, these are just matrices that are symmetric about the main diagonal. That's all they are. A is called, A n by n is called symmetric if A is equal to A transpose. That's the definition. And basically what that ultimately means is that it has some visual symmetry, that when you look at it, you can see it's symmetric about the origin. So note about the main diagonal. This is equivalent to saying visually and otherwise, I guess, it is symmetric. In your usual understanding of the word symmetry about the main diagonal. So, example, if I have any random matrix that looks like main diagonal could be whatever, A, B, C, and let's populate this E, F, G. Right, so that's the main diagonal. There should be a symmetry. So if I look over here, this guy must be an E, and this guy must be a G, and this guy must be an F. Oh, the other way. This is the G, that's the F. Right? So notice that the first row is the first column, the second row is the second column, the third row is the third column. Right? So if I take its transpose, I get the same thing back. It's kind of saying that the diagonal elements can be whatever they want, but the other elements must be mirror images across the diagonal. And any such matrix that has this property is called symmetric. They allow us to do a lot of cool stuff, but for us, we'll just need to know what they are and how to prove little things about them. So you should be able to know what they are, and I think your homework will go into this a bit. You should be able to prove some simple properties about symmetric matrices. For example, if I told you two matrices are symmetric, is their product symmetric? Is their sum symmetric? Things like that you should be able to justify. Right? You should be able to figure out yes or no is the answer and prove it. Right? Definition, A n by n is called skew-symmetric. I believe another phrase for this is anti-symmetric, but I can't remember at the moment. If A is equal to the negative of this transpose. So symmetry is a nice thing. There are properties that you can attach to symmetry that can determine, for example, when matrices commute. Like when is A times B the same as B times A? If you can express them in terms of symmetric matrices, you can see right away if this is possible. And it'll tell you, there are a lot of things that you can link to this and a lot of reasons, even more theoretical reasons why this is important, but we're not really going to delve into those. So just know the definition. It means it's symmetric about this. So if I ask you to prove something about the set of all 2x2 symmetric matrices, you can assume that they all have the form something similar to this, right? And you can manipulate a proof by manipulating objects that look like that, right? Or I can say, prove something about the 3x3 symmetric matrices, and if you're going the brute force way, you can assume they all look something like this, right? If I say to prove something is true about symmetric matrices in general, you'd have to kind of work with this equation, which doesn't have a size, and you'd have to prove that and prove whatever I'm asking in general. But yeah. So you won't do anything terribly important with them, but they are important for much later. If there was a second linear algebra class undergraduate, they would definitely be a chapter unto themselves. Yeah.
If for skew-symmetric, if you negate the transpose, and doesn't that mean the main diagonal has to be zero, all zeros?
No?
For A to be minus A, and B to be minus B? Am I misreading, am I misunderstanding that?
No, the main diagonals, they are never actually mirrored across anything. They stay fixed.
They stay fixed, but they're negated. So
You're saying they have to be zero? I don't think that would be the case.
It's in the sum?
Come again? No, that's the definition.
okay.
to get back to you.
You're saying when you add them up, right? When you're adding up the A and the,
Well, if you take that A,
and you're adding it to its
you transpose it and then you multiply by -1 everywhere.
Like each of these, he's saying would be multiplied by a -1.
yeah.
If they're going to be equal, A has to be equal to -A. B has to be equal to -B, and C equal to -C. So they have to be 0.
That's possible. Seems to make sense, but I don't recall that being a part of the definition. Maybe it's implied. So that ends what we want. I believe we spoke about skew-symmetric in 1.5. So this was just a little thing I picked out from 1.5. And that actually ends everything we want to do from chapters 1 and 2. So everything in the syllabus in chapters 1 and 2, you can try the homework problem, which I should mention that. Remember, online homework is not enough practice. Attempt to select the suggested problems. Especially the ones dealing with proofs. We haven't created AI that can read and understand proofs yet. So, for the foreseeable future, mathematicians are safe from the AI revolution. The robots will always need us.
I saw some
Like almost everyone else, like you guys are expendable. But a robot can't be creative in the sense of being able to write a proof and understand that there are many different ways to phrase the same thing, many different routes to the same path that are not always a direct application of logic but require some sort of creative use of logic. So be sure to actually practice the problems from the suggested problems from the homework, especially the ones dealing with proof. The online homework should cover most of the computational things you need to know, but if I'm going to also ask you proof-based things, prove that if this is the case, then that is that. I might ask you to prove a little part of the equivalence theorem, like prove that this if and only if that, and I choose two random things in the equivalence theorem. You should be able to do that, and things of that sort. And you'll see things like that in the homework. So be sure you're actually practicing that from the textbook. Okay.
I have a question. I noticed that some of the proof questions in the text don't actually have answers in the.
I think most of them won't.
Yeah.
So I guess.
Is there like a resource that might sort of at least give the answer so you know?
Yeah, a lot of the research that I gave you in the beginning can help with that. So there are math forums, Math Stack Exchange. You can ask questions there, and people can guide you. You can see me during office hours. You can. A lot of the times, the proofs in the book, you will find those same proofs of those things somewhere else, right? Especially if it's a very typical and reasonable question to be able to ask. You know, like the question I randomly asked here. Okay, you know about symmetric matrices. What if you multiply two of them? Is that symmetric? Odds are there's going to be a proof online somewhere of someone proving that. Because that seems to be a natural thing to want to know. Like how is symmetry maintained when I add stuff, when I multiply them, blah, blah, blah. So a lot of times you'll also find proofs online. If you don't find the exact proof online, you can go to one of these math forums, say, okay, I'm working on this proof, this is what I have so far, any suggestions on how to continue, all right, this is what I did, is this right? Or you can even ask me during my office hours, which is usually after class. For the most part, if you're following the rules of logic correctly, you'll kind of know that you're right based on, if you know that you're justifying every step, I can say I can do this because this theorem over here and this applies here, and then I can do that. If you do that and you get to the end result of what you know should be the result, then you're right.
And then just a follow-up question. I noticed that some proofs, like some of the proofs that are proved out in the book, use arithmetic to sort of express the proof, whereas others just kind of are a paragraph. Is there sort of a method of understanding when one is appropriate over the other?
No, not really. It just depends on. It just depends on the question. There are times when the proof requires you to know what's happening to each individual entry, whereas sometimes you just want to know if something's happening on some sort of global basis. And that's kind of what's going to be the determining factor. As well as the fact is there are some things you can get away with saying in general because there's some direct property that applies. So for example, there's a property that talks about if you have a symmetric matrix that is invertible, then its transpose is also, what was that thing again? No, like if a matrix is invertible, its transpose is also invertible. And you can get away from brute force with that because there's a property that tells you that you can do this, right? And using that property allows you to get away from having to compute adjoints and worry about what's happening to each individual element, because now with this, you can throw in an inverse matrix here. That guy's going to apply here. And once you're looking at inverses, the order doesn't even matter, so you don't care that the inverse came first or second. And so that allows you to say, no matter what size it is, this is going to work out. But if you don't have some sort of overarching property that can apply to what you're saying, and you have to somehow show that individually all the entries are going to be in the position they're supposed to be and perform the function that they're supposed to perform, then you're going to have to kind of brute force it and write out some sort of thing with ellipses and show the process. And it really depends. There's no general rule. It's just a matter of, is there some property that we've already proven that can apply a broad brush here or not? If not, odds are you have to brute force something.
So substitution inside of a known property is an acceptable proof. Like you don't
Yeah,
have to prove
substitution
that
inside of a
property.
known property. Once the thing you substitute fulfills what the property says it has to fulfill. So if there's a property about square matrices, you're not allowed to substitute a non-square matrix into that to prove anything. So as long as you have a property that says this applies to all matrices that fulfill these cases, you can swap things into that at will that fulfill those cases, and that can help you bypass something. But that's the nature of math at this level. There's nothing I can say, oh, you can always do this, or this is always the strategy. It's just, it's not true anymore. You know, math for which that's true, we call elementary math. We're no longer in elementary math, we're in advanced math.
Sucks for the AI.
That's,
For now.
yeah. Okay, so now we are going to move on to, Leo got back just in time for the interesting part of the class. We're going to move slightly away from computation now. We're going to start talking about much more theoretical and conceptual things. So it's chapter 4 where we're going to talk about vector spaces. So we're going to do 4.1, it's titled real vector spaces. So odds are in your book when they're talking about vector spaces, they mean real vector spaces. Some things I might say in general, but if you're going from the textbook or doing something on a test, we'll be talking about real vector spaces. And I'm going to explain what that means. We need some definitions though. Definition. Let A be a set. Right? We know sets are collections of objects. An operation on A is a function whose inputs and outputs are elements of A. To top this off, a binary function, a binary operation takes two, specifically two elements of A, and outputs one element of A. So we're going to talk about things, we're going to define them in terms of operations, and the binary operation is important to us. It will take two elements and output another element. Example. Plus is an operation on R. The usual arithmetic plus is an operation that takes two things and outputs one thing. So you can think of this as something like 1 plus 2 equals 3. Basically what we're saying, there was a function that when you plug in 1 and 2 into that function, the output is going to be 3. It's just going to be some rule that according to some convention that you define will take two things from your set and connect it to one other thing in your set. Such a function is called an operation. Now, we're going to talk about something where I intentionally have to give you a fuzzy definition, because to give you any specific enough definition for this thing I'm about to define, we'd have to do a whole thing in abstract algebra. It will take like a couple lectures, well, a lot of lectures, to be able to just state this definition. So we're going to treat this one kind of fuzzy at this moment, but we're going to use mostly our intuition here. The definition is the definition of a field. A field is a set with two operations on it. With two binary operations called addition. I'm putting in this in quotes for a reason, so stop thinking of addition as the usual arithmetic addition, unless it's stated that way, and multiplication. So that, and here's where the fuzzy part comes in, because to be able to really say what this means, we have to talk about a bunch of axioms, define a bunch of things, talk about what a group is and what a ring is and blah, blah, blah. But the fuzzy way is going to be the set with these operations. Behave like R with plus n times. And at this level, that's the best definition I can give you. So you're going to take it to be an intuitive definition. Luckily for us, the only field we're going to care about will be the real numbers. That's why we're going to focus on the real vector spaces. That's what it means. So vector space where the field under consideration is the real numbers. So it's not like they're fake vector spaces. Like the real in that phrase, real vector space, refers to the fact that we're using the real numbers as the field. But a field is literally any set that will have two operations that they behave exactly like addition and multiplication on the real numbers. Meaning, whatever functions we define here, they're commutative, right? They're associative. One distributes over the other, so they're distributive laws. I can divide by any non-zero element and get a meaningful element, right? That's not always true, right? So for example, the integers is not a field, right? Because if I divide two integers, I don't necessarily get another integer, right? However, if I divide any two real numbers and the denominator is not zero, I get another real number, right? So the integers does not behave like the real numbers, right? So in other words, if you're looking at anything and for point by point it behaves just like the real numbers, it's a field. If something that you can do with real numbers can't be done with this thing, it's not a field, right? So the set of matrices is not a field. Why?
You can't divide?
You can't divide. There's no such thing as division. Another reason why it's not a field.
You can transform the size of the matrix with matrix multiplication.
You can transform what? Well, matrix multiplication is an issue. Why is that an issue?
Because like say that you have like a 2 by 2 and like a 2 by 5, and then the output would be something between 2 by. Is that allowed?
Yeah. What if I restrict the size of my matrix? Let's talk about all 2 by 2s only.
They don't commute.
Multiplication does not commute. I know in the real numbers multiplication commutes, right? So this fact, it doesn't behave like the real numbers. A field is any set with 2 operations that when you apply these rules, it behaves just like the real numbers. Everything I can do with the real numbers, I can do some analogous thing to this set, right? So any set that fulfills these properties, we call it a field. And to say it behaves like the real numbers is something that really needs to be defined, but it's a whole other class. That's abstract algebra. That's not what we're about. Okay. Here's another definition. The elements of a field are called scalars or constants. Right, so I say, oh, multiply by a constant. We multiply by some element in a set that behaves like a field. So now, of course, at this point, the only fields that you've been exposed to at this point would be like the real numbers, the rational numbers, and the complex numbers are all fields. All the other number systems you know of are not fields. The natural numbers are not field. The integers are not a field, right? Because you can't do everything with them that you can do with the real numbers. Okay. What else? So we know what an operation is. It's basically a function that allows us to combine two things. I give you two things, you do some rule with them, and you give me back one thing. You can talk of this as combining two things. Definition. I'll probably need to define a vector space first. Okay, so now let's get to the titular object of this section. We are going to define what a vector space is, which I did in the first lecture, but we're going to talk about in more detail here. A set V with two operations, which we will call addition and scalar multiplication, is called a vector space if the following hold. Okay, so we're going to define a vector space. One, for all UV in V, U plus V is in V. Right, so addition, just to confuse people, use exactly the same sign as regular addition, but we're not thinking of it that way all the time. This is called closure under addition. Two. If I take U plus V plus W, Right, so remember we're looking at a binary operation here. They're binary operations, meaning they take two inputs and outputs one output. So you have to worry about what if we have more than two inputs. What happens is you compute them two at a time.
Okay.
And it says that we can compute the two at a time in any order. This is called associativity. This is for all U, V, W in V. And this is called associativity of addition. Or you can say the operation of addition, whatever that means in this context, is associative. Meaning the operation is defined for two things, but if you have more than two things, you can still make it meaningful by just doing two at a time, and you can do it in any order that's sequential. U plus V is equal to V plus U for all UV. That means addition is, what's the word for this?
Commutative.
Commutative. Or there exists zero in V. That is, let me write this down. There exists an element in V called the zero vector. And denoted by this symbol such that if I take U plus 0, I get U.
Does it also have to be unique, or?
It has to be unique, but it is not in the definition. You can prove that it's unique. Okay? That's an extra theorem that you can prove as a separate problem. Basically, the idea is if you pretend that two guys satisfy this property, they'll end up being the same. Okay. So there exists such a guy called the zero vector. Right? Doesn't specifically have to do with the real number 0. It's just some element where this is notation for it that fulfills this property.
That's an element in the set.
And it's an element in the set. It has to be in the set itself. 5. For every U in V, there is an element denoted minus U in V such that U plus minus U gives us the zero vector. Minus U is called the negative of U. Six. Let F be a field. Remember, that's just a set that behaves like the real numbers. And K and element, K and L are elements in F. Then KU is in V for every U in V. This is called closure under scalar multiplication, and I'll define more what scalar multiplication is. Scalar multiplication is a binary operation, but it thinks of two sets at a time, right? It takes from the set V as well as from a set F. So it takes two elements from two different sets. It takes a scalar from a field, and it takes a vector from some other set, and it combines them and creates another vector. So it's still a binary operation, but it takes inputs from two different sets. One of these sets has to be a field. And whenever we do such an operation, it's called scalar multiplication. 7. Scalars distribute across vectors. So a distributive property holds between the elements of the field and the elements of the vector space. It also works that if I have a sum of these scalars, that will also distribute across these guys. So that'll be Ku plus L. 9. Taking k times a scalar of a vector, scalar multiple of a vector, is the same as taking the product of the scalars times the vector. And finally, the most perplexing property of all, 1 times u equals u. Where 1 is in F and satisfies the property. Meaning, this is a notation. I mean, for us, when we see 1, we're going to think of 1, but in general, it's a notation. Satisfies the property of multiplicative inverse, multiplicative identity. So any set with two operations that fulfill these 10 properties, we will call such a set a vector space. Let me define more for you now. The elements of a vector space are called vectors. Right? Again, it's just a proper name. You don't necessarily have to think of vectors in the sense of physics or Calc 3 that you've done. They can look like anything. They don't necessarily have to have magnitude or direction. They just have to be elements of a set that will fulfill these properties under some arbitrary definition of addition and scalar multiplication. Definition. Scalar multiplication is basically a function that combines a scalar and a vector to give another vector. You can think of it as V cross F, and it outputs something in V. Means these are all coordinates of vectors in V and scalars in K. So its input is some sort of coordinate where one of them is interpreted as a vector, one of them interpreted as a scalar. This is a member of a field, this is a member of a vector space, and the output is some other member of the vector space. That takes a scalar and a vector as inputs. Outputs a vector. So there's the notion of something called a vector space. This is just a set with two operations, addition and scalar multiplication. Addition is a way to combine two elements in that vector space to output a third element. Scalar multiplication is a way to combine a scalar and a vector and an element in that vector space to get some other element in the vector space. These can be arbitrarily defined, but if they're defined in such a way that all these 10 properties hold, some of them are erased at this point, then we call that set a vector space. So it's important that all these little pieces, which again, it's not elementary math anymore. One definition leads to you having to know a bunch of other definitions. It's not just one thing. You can't just say a vector space is a set. That's not enough information. You have to tell me who's the set, who's the field, how are the operations defined. I have to tell you a bunch of things to describe a vector space. I can't just say one thing. Like if I give you a set, oh, here's a set. Is it a vector space? I don't know. Who are the scalars? What are the operations? How do I combine people here? Right? You have to give me a whole laundry list of things. It's not such a huge laundry list, but you have to tell me a bunch of things for me to know. One set could be a vector space with respect to these operations, but it's not a vector space with respect to other operations. And that's not uncommon. So you have to really think abstractly here, and you have to take a bunch of things into consideration all at once. So you might be thinking, oh, and especially with my notation, oh, it turns out that the vectors that I learned about in Calc 3 fulfill all these properties. And yeah, that's kind of where it came from. So remember what I was saying in the beginning when we were talking about functions, about a set that we know a lot about, and there might be a set that we don't know a lot about, but we can connect them with functions, and so if the function has a certain property maintained, I can know about these guys over here. So basically you come up with a definition that distills all these central properties of a set that you know a lot about. In this case, the vector space that we learned from physics, right? We know a lot about that guy. We can do calculus, we can do a whole bunch of stuff on that guy. And so we want to know, if we discover some other arbitrary set out there that behaves like this guy, we want to know about it. We want to know how to define it. And it might not look like the guys might look different, they might combine differently, something might be different, but essentially when it comes down to these essential characteristics, it behaves just like the vector spaces that we're used to. And that can help us to do research on this new arbitrary thing. And so that's sort of the idea. So a lot of definitions will look like things that you're familiar with because that's the point. We're familiar with them. So we get their essential characteristics and make that a definition and try to discover if there are other things in the universe that we don't know about that have the same behaviors, that have the same characteristics. And so we can make predictions about them, we make calculations with them, and all that stuff. So that's where this is kind of going. So we know a lot about vector spaces in the formulation of Calc 3, but there might be other things, and there are other things. So let's actually do some examples so that we all under the same page. Examples and non-examples. Okay, give me an example of a vector space. Oh, one other definition just to, because I'll say the phrase all the time. So I want you to know what I mean by that phrase. So to define a vector space, we need three things. A non-empty set V, two operations, which we call addition and scalar multiplication. Right? This guy allows us to combine two things in V and get a third thing in V. This thing allows me to combine something in V with something in a field and get another element in V. 3, you need a field. Call it F. And so those are those things. And so, and with these given, can say V is a vector space, we use the word over F with respect to the operations. Okay. So let me give you an example of such a phrasing that I can say to you now. So examples and non-examples. R2 is a vector space over R with respect to vector addition and vector multiplication. I can make this statement. With respect to vector addition and scalar multiplication as defined in multivariable calculus, R2 is a vector space over R. Meaning, I'm thinking of a set of two-dimensional coordinates. My field is the real numbers. And with respect to the usual way we define vector addition, which means you add things component-wise using arithmetic condition, and scalar multiplication, which means you multiply things component-wise using arithmetic multiplication, this is a vector space. If someone says R2 is a vector space, they said something nonsensical. Because they have to tell you who is the field, what are the operations. Yes?
Is R a vector space over R?
R is a vector space over R. So a set can be a vector space over itself. If the set happens to be a field, you can have it be a vector space over itself. So R is a vector space over R, R2 is a vector space over R. In fact, Rn is a vector space over R. And now I'll refer to the arithmetic plus and times as the usual. So that's another example. In fact, we could create, these are vector spaces. We'll talk about dimensions later, but this is an nth dimensional vector space, we'll call it. I'll define to you what dimension means in like a few sections. I think in 4.5 we talk about that. But there is a possibility of even creating an infinitely dimensional vector space. R infinity is something that we can define. It's the set of all coordinates of infinite length where each component is a real number. And it's a vector space over R with these operations. Tell me something that would not be a vector space. What about the integers over the integers? Is or is not a vector space?
Not.
Why not?
The integers are not a field.
It's not a vector space. Since Z is not a field. Exactly.
What if we
Okay.
had,
What about the integers over R?
I think it would be.
What about Z over R? Vector space or not?
No,
No? Why not?
because if you multiply an integer by some a rational number, then you don't get an integer.
Exactly. So there is no closure under scalar multiplication. Property 3 or 4 or whatever that was fails. So even with usual addition and scalar multiplication, I don't want to write times here. I'm tired of writing. That's not the right operation. Usually you use the times to say you're combining two vectors, but you want to combine the scalar and a vector here. Since if n is in R and n is not rational, or heck, not an integer, then n times x may not be z. For x and z. And I can give you a specific example here. If I take radical 2 times 1, it's not an integer, right? So this, I just did a scalar multiplication. I can multiply an integer by the scalar, and I do not get another integer, so it's not a vector space. What about this one? R over R. With the operations. So now I'm going to define to you what I want addition to mean in this context. U plus V is UV, regular multiplication. And so that's for all UV in R. So that's me defining addition. I'm going to define scalar multiplication in this way. K times U equals U raised to the K for U in R, K in R. And so this is the field. Let me just vector space. If I take this weird definition of addition and scalar multiplication. So pretty much I took two arithmetic operations and I changed them to two other arithmetic operations. Think of addition now as multiplication and think of multiplication as exponentiation. Does this mess up its vector space properties? Yes or no?
I think so.
Well,
No.
why not? You have to justify it.
Because even if it doesn't have like a regular addition,
Mm-hmm.
it's still, U times V is still in R.
Sure. That's one of the properties.
Yeah.
The exponentiation commutes, I guess.
We do not require scalar multiplication to commute.
Oh.
So that's not a thing. The addition would commute, clearly.
Because arithmetic.
Because multiplication commutes. If I take two real numbers and I multiply them, the result is a real number, so it's closed. What else do we need? Associativity, real number multiplication is associative, so that's fine. What about 0? Who's the 0? So properties 1, 2, 3, okay, pretty clearly, because the multiplication has all those properties. But what about property 4? Who's the 0 here? Is there a 0? Because if it doesn't have a 0, that's bad. It's not a vector space anymore.
It's because UV would.
1 is the 0. The real number 1 is our 0 vector. What? What's the definition of 0? Why is 1 the 0 vector here? how do you define 0? 0 is the guy that when you add it to someone, you get itself. Right? Since if I take 1 plus some arbitrary vector, by definition that is going to be u times 1, that gives me u. So I added something to the vector, and the result was the vector itself. So 1 is the 0 vector here. So I change the operations. It might not change the fact that it's a vector space, but it can change the identity of who plays what role. Let's do another one. Who would be the multiplicative identity? So there's property 10 that says 1 times u should be equal to u. Who would play the role of 1 in this case?
0.
It'd still be 1.
0.
1.
It's still 1. Okay, so that makes sense. What else do you think might fail here?
Does scalar multiplication distribute across addition?
Does it? How would you know?
I don't think it would.
Let's check it. What number property that is? Because I don't remember what number.
Okay.
What property did I write down? Because just so you can match it up. 7?
Yeah.
So let's check 7. 7 says that if I have a scalar and a sum of 2 vectors, then what has to happen?
It's equal to.
It must be equal to this guy plus that guy. Right? So let's check that. Does that work in this case? If I redefine my operations in this way? Well, let's check. K times u plus v is equal to, how did we define addition?
U times v.
And how did I define taking a scalar multiple of the vector?
It exponentiates.
It exponentiates that. Now we're in the realm of regular arithmetic. Multiplication raised to an exponentiation is that.
Okay.
But what is that? That by definition is going to be my u to the k plus v to the k, if I'm thinking of them now as the vectors. And that by definition is this. So that works.
Okay.
Turns out it is a vector space. You can go through each of the 10 properties, and the identity of who plays what role might change on you. Remember I was making that analogy to, oh, it's the witness protection system. People change their names, but they're all the same people. There is someone there that does all the same things of all the people you're familiar with doing. They might change their identity on you, though. It can depend on the operation. You can check all of them. This is a vector space. Finish the check. Right. You can go through all 10 properties and you can convince yourself that, yep, these all work. So swapping these operations, it might make things a little weird to think about, sure, but it fulfills all 10 properties. We have the 0 vector, we have negatives. Who's the negative? That's another interesting one. Probably we'll check that. Who's the negative? How did we define negatives?
It's the guy that gives you back 1.
Yeah, u plus
Zero
negative u
vectors.
equals 0.
Right. So let's check. I don't know what property weird. Right. So there exists a negative u in V such that u plus negative u should give me 0. Right. Now remember, in this case, our 0 is 1.
So it would be the reciprocal, the
Zero.
negative.
It'll be the reciprocal.
But if addition is multiplication.
Come again?
If what we're calling addition is really like our usual multiplication.
Yeah. Which now reminds me, I should have, because I want to take reciprocals, I should probably only say the non-zero real numbers.
If you take the reciprocal of the thing and multiply it, don't you get 1?
Exactly.
Oh, because 1.
And 1 is 0.
Yeah. That's crazy.
So for, we should put positive real numbers. Okay. So it turns out in this set 0, the real number 0 is not in the game at all. Right? So you should define this as positive real numbers. So this is, notice that if I take u plus, say, the vector 1 over u, that gives me, by definition, this multiplied by that, which gives me 1, which is equal to the 0. So for u in our positive, negative u, that vector is the reciprocal of u. Okay? So if I define the operations this way, it turns out that negative becomes reciprocal. Right? It turns out addition becomes multiplication, and scalar multiplication becomes exponentiation, but the vector space properties are still defined, meaning if for some reason I need to redefine my operations in this way, anything that applies to a vector space, any kind of thing I can do with a vector space, I can do here. Yeah.
Sorry, how do we know the second thing's defined? Like 1 over u, is that?
Because it's in R plus.
Like the 1 over u, that's a vector.
Yeah, 1 over u is the regular number, the reciprocal of u, according to...
No, I'm saying the previous stuff, like before the equal sign, like on the left-hand side.
Yeah?
Yeah, but the second term.
Well, this is the negative. I was just emphasizing that that means this in this context.
Okay.
I have a quick question.
Yes.
Because when you're in this when you create these rules, like I said, vector u plus vector v equals, vectors u times v. When you're saying that multiplication, you're referring to like, as in multiplying two vectors, or like what kind of multiplication you're referring to?
Arithmetic multiplication.
Okay.
I believe I wrote that down. If not, you can put that in.
Okay.
And I should have said we're only on the positives because the number 0 is not going to be involved here at all.
Yeah.
Right, because with zeros you're going to have division, as well as the 0 will kill all your information, because if you add that 0 to anything, it kills it. See, are there any other nice examples I can do? Well, set of n by n matrices is a vector space. What about the set of invertible matrices? Let's say I say the set of 2 by 2 invertible matrices. With matrix multiplication, as we defined it earlier, and addition. Right, so my addition is matrix addition, my multiplication is matrix multiplication, and I'm looking at the set of 2 by 2 invertible matrices. Do they form a vector space over R? Which means my scalars are R, the entries in my matrices are real numbers. Vector space? See anything that might break?
Addition.
Addition.
Yeah, if you add, I don't know if you add two invertible matrices, is the sum still invertible?
I don't know, is it?
I don't know.
You guys tell me. Is it? It's 2 by 2. It should be not so bad coming up with an example here. Okay, give me a 2 by 2 invertible matrix. Just give me a 2 by 2 invertible matrix.
1, 2, 3, 4.
1, 2, 3, 4. How do you know that's invertible?
We inverted it a few classes.
How would you check on the spot if it showed up?
The determinant is non-zero.
Determinant is not 0. This times this minus that times that is not 0. So I know it's invertible. Give me something else that if I add it to this, I won't get something invertible. Can you think of such an?
Or negatives.
All the negatives. Guess what? That's also invertible. You can check. Determinant is not 0. Add these two, what do I get?
Zero matrix.
Determinant is 0, not invertible. So it turns out it's not a vector space. Because when I add two things in the set, I don't always get something in the set. I can add two invertible matrices and not get an invertible matrices. So it's not a vector space according to these operations. Turns out the set of all 2 by 2 matrices, if I just take all 2 by 2 matrices, no discrimination, it's a vector space. It will fulfill all 10 properties. What about symmetric matrices? Oh, that's a nice one. Form a vector space. If I take 2 symmetric matrices and add them, do I get something symmetric? If I take a scalar multiple, do I get something symmetric? Who's the 0 vector? Who's the negatives?
I think they would be a vector space.
It would be a vector space, and you can go through and check all those properties, right? So invertible matrices don't form a vector space, but symmetric matrices do. Set of all matrices do. If you're looking at something like, to take a computer science example, Boolean arithmetic with 1s and 0s on and off, thinking of plus as or and times as and do like an and not gate kind of thing over the integers. Turns out that's a vector space. Pixels on a computer screen form a vector space if I define it to be a vector space over color. Let's say I take the set of prime colors, blue, what are they, blue, yellow, and red. I can form any color with these 3 colors, right? The set of all possible colors that I can, and scalar multiplication here is me mixing some proportion of a color, right? So 2 blue plus 1 red means I take 2 parts blue, 1 part red, mix them together and get something else.
Pixels are green.
All possible colors. Huh?
Pixels are green, not blue.
What?
Never mind.
It doesn't. I'm saying a color, I switched the example. So a color map, the set of all colors. Vector space? What do you think?
Yeah.
Okay, what are all the properties? If I mix 2 colors, I get another
Wait,
color.
what's the
That makes
zero?
sense. Who is the 0?
Yeah.
Who is the 0 color?
You can undo a color.
Right? If you have the color blue, what's its negative? So assume you pick a color that's the 0.
I think from art class.
What are you
it's
going to
like
mix with blue to get nothing? How are you going to get what mixed with blue gives you no color?
Black, orange.
It's not going to happen. It's not a vector space. There's no 0 vector. There's no negatives. What is the negative of a color? You can't do it. It doesn't make any sense. Electric currents through a circuit board. Vector space? Can I think of the set of all electric currents through a certain circuit board as a vector space? Well, who in here is good with physics? I don't know. Well, the answer is no. I'm not good at physics, but there's something called Kirchhoff's law, which kind of breaks the whole vector addition kind of thing. Right, that says the amount of currents coming into a certain point must be equal to the amount of currents out of a certain point, and that kills the scalar multiplication of the vectors. So if I think of these 2 guys as vectors coming in, turns out that the vector going out won't fulfill the vector addition properties. So you can think of a lot of things. You can go through nature and start to think about stuff. Is this a vector field space? Is it not a vector space? And a lot of things can be interpreted as vector space, and when we can do that, we can do a lot of interesting things with them, and some things can't. And we'll stop there. So remember, our test is on Thursday. It'll cover everything we did up to today, including being able to verify whether something is a vector space or not. And I'll post a review over the weekend.